Yeah, so I hope both online and offline is all working. Great, so awesome to be here. The talk today is going to be about engineering of research by horizontal and vertical integration. Since we are not, I'm going to do mostly a talk about the infrastructure and all the things that we developed around, because what I want to give you is a bird's view, this is why I put the bird here, of the research processes and how I think we can engineer them to make them faster. I believe this is agnostic to what you're intending to do, be it battery research, catalysis, or electron microscopy for that matter. And I'll just do a little bit of results at the end. So if you want to visit us, so we are, it's technically University of Munich, but you know, Munich is, or TUM is one of those universities that has quite a lot of different research campuses. We are in Garching, so we have the beautiful labs in the CRC, so that's a catalysis research center, and our offices are there on the site in this ugly old, we call it internally the castle. So we do lots of different things, mostly relating to robotic experimentation. We're setting up a lot of new instruments. We try to repurpose some old instruments, and I think that overall what we do is mostly really just creative work. So if you were to go into our lab, this is just a picture I took a couple of weeks or even months ago. You'll find a situation like that, and I believe that even though your research might look very, very different from what we do, I think fundamentally what we really do is we're just cooking. So this is just an example of a small street kitchen, and unfortunately the beamer here is, so the people online can see much more. Essentially you can put down a order to a kitchen, you have a cook, and then you have a small kitchenette. So this is a smoking barbecue taxi. So they actually have their barbecue inside a motor hood. And fundamentally, how I view the whole research process is somebody, let's call this A, has some idea of, hey, I want to do an experiment. You have something where you could say like, okay, I need to translate some order into something, like, okay, I need to heat up an oven. And then you have the actual instrument. And then, of course, your instrument needs to be able to tell you, like, okay, I'm heated up. And of course, you also need to be able to tell your customers what you do. So the way how we typically automate our lab is we have some JSON-like instructions. This can be relatively high level. So I don't know, in this case, it would be make me a garlic naan. And then we need to translate these higher level instructions into a sequence of events. So these are actions, for instance, whatever, you can make a dough, you can prep an oven. And then you need to be able to translate these still relatively high level actions into things that are more atomic, such as you need to heat up an oven. And eventually your oven will need to tell you like, okay, I'm heated up now, please continue. So to bring this a little bit back from the kitchen to, and sorry if this is now bright again, to actual research, we wrote, John Gregoire and we wrote a review a while back on the fundamental research actions that we do in research. So if you ask me, essentially anything that you do, including all the things that I do, I could probably classify in these like 7 or 8 different research actions. That is, you typically plan, you synthesize, you process, you characterize, you interpret, you do some quality control, hopefully, data management, hopefully, and then some performance evaluation. And it doesn't necessarily need to be in that order. You can do some planning. You can maybe even put quality control right after planning. A synthesis might follow after whatever performance evaluation. So the way how you arrange these research actions is up to you and can look very different in your specific domain. What most people, at least in my field, which is like the high throughput experimentation world, then do is they deploy accelerators. So this is all the stuff here in green. That could be automation. So or parallelization. Parallelization is actually the easiest way to accelerate any kind of research. Yeah, instead of putting one sample in the oven, you put 2 or 3 or 5. And by that, you achieve some factor of acceleration. We have machine learning models. We have active learning. I will go a little bit into what this means in our context. And then you have automated reasoning, which is, at least in the experimental field, not there yet. And then you have a new kind of thing. This is called engineering. And hopefully by the end of the talk, I can explain to you a little bit what this really means. So how do we deploy this kind of automation to both synthesis and characterization and performance evaluation? So my group works a lot with the scanning droplet cell. This is just a random picture. Explain it in a second how it really works. What we have here is essentially different kind of experimental campaigns. In these campaigns, we translate essentially into a checklist. Yeah, so for this device to measure something, we need to move to a sample. We need to perform the measurement. We need to analyze it. We need to shove it up to some database. And so on and so forth, and then maybe even act on the results to do active learning. The way how we do this is with a Python library called HELAO, stands for the Hierarchical Experimental Laboratory Automation and Orchestration Framework. The basic idea here is that any action and any driver, where drivers are your really low-level atomic kind of devices, they are all servers. Let me put my phone, because people are writing me messages. So all of these drivers, all of these actions are web servers. The reason is this way we can have different hardware run on different computers and still be able to bolt them together in software, just as we would do in the physical world. You know, in the end, I just want to have a screw in software to bring together a potentiostat with a force sensor, with a pump to build a new kind of device. So scanning droplet cell works roughly like this. You have a miniaturized electrochemical cell where you place your counter electrode in this small housing. So here you have a picture. So this the substrate is 5 centimeters big. You have a counter electrode, you have a reference electrode, and a very small volume for the electrolyte. And you only expose about a millimeter in diameter of your substrate to perform an electrochemical experiment. What you can then do is you can do sequential experiments, meaning every time your a scanning droplet cell touches down, you can do a new experiment, you can exchange the electrolyte, and it's relatively cheap in terms of how much material you really use, and how much, let's say, real estate in terms of a substrate you really need. You can have different positioning systems and do all kinds of things. So here's an example from our old lab in Ulm, where we actually placed the scanning droplet cell in a glove box. So the glove box is so big that you don't see it here. But if you do this, you can work with nasty electrolytes. So the liquid that you see here at the bottom is LiPF6 containing battery electrolytes, forms HF under contact with moisture. What we can do here is, because we go with this approach of having essentially small web servers and a sequence of action, we can go in and just say, hey, okay, today I want to hook up a webcam with maybe some object detection together with a motor and a potentiostat. And what I want to run here is I want to run sequential experiments for whatever battery materials, analyze them in real time, and act upon newly incoming results, which I think is super cool. Again, really the technology that underlies or that underpins all of this is a fast API with a nice Python backend and frontend. So we are able to achieve quite nice reproducible results for very, very little materials, or very little material need. This little yellow material here, this is actually gold. So just to show, and because gold is nicely reproducible in terms of sputtering, we produced here 36 gold anode batteries, and our Coulombic efficiency, our discharge capacity, they are all relatively within reason, within a relatively small error band. And what we can add to this is we can also add this object detection. So one major issue with the scanning droplet cell is leakage. So we can run these experiments, and then if we detect, for instance, a leakage of the electrolyte where it's like flowing out, we can act accordingly, and we can, for instance, then pump back the electrolyte and do things like that. So this is relatively easy. We do it a little bit more complicated. That is here for the production of coin cells, which you might know from a car key or a watch. So here we have the individual components of a coin cell laid flat out here on these orange trays. We have these different robots, and all of these instruments, including the crimper and the rail, these are all web servers where we send different JSON commands to. They execute it. They tell us if they are done with the execution of their of their task. We can even do things where we take a picture. So this is just another webcam. We take a picture of a component that we grab. So in a second, you should see that it lights up again. And when we take such a picture, we can do some live data analysis. So for instance, what it did here is when we picked up that piece of an anode, in this case, we always pick it up slightly off center. And then when we take a picture, we do an automatic edge detection, and then we can place it perfectly in the center. So we are actually really well reproducible in terms of how we place the different parts of a cell. We always take pictures before and after, because very often when you think you placed it correct, you actually don't. We don't care about the placement of the separator because that's anyway not reproducible. So what you get in the end is you get batteries, okay, cool, but you also get not just data lineage, you also get sample lineage. So why is this important? You could probably, the further away you sit, you can maybe tell that there is some slight variations in the gray tones here. If you sit very, very close, you could maybe even see that there are some cells with like spots on them. So this is cool because now we can do something that very few battery researchers that make this by hand can do. We can actually, we know which cell this is. So if we see during the formation or during cycling some weird electrochemical behavior, we can actually go in and pinpoint it to some certain kind of defect. Or if the electrode is like weirdly wrinkled, we typically see this in the electrochemical data. And of course, we always put this online if we are allowed to share it. So I believe that here I'm preaching to the choir if I say this is super important, that you shouldn't just keep track of how you analyze your data. You should also keep track of how you, of what you did to your samples. So this is from a relatively old publication we did at Caltech, where we did not just keep track of the experimental data analyses that we did. So the idea was always whenever we have a plot and a point in that plot, we could always trace back to essentially what kind of gases, what printer, and what precursors we used. That worked sort of. So by the way, my official job title back then was I was the materials data engineer. So what we set up is this gigantic database with the idea of being back then, so it was called MEAT, of being something like the experimental equivalent to the materials project. Because JCAP is no more, so it was sunset, I think 2 or 3 years ago. The website is also now defunct. But my biggest learning from this was you can have all that nice data management you want. You can even have a nice interface. This is all fine. But if your internal software with that you do the analysis is not easy to use, you win nothing. So why did we even have that software? Well, we were a high throughput group, but only about half or 1/3 of the people being in that group really even knew how to program. But what we knew was most of the analyses, if you here just analyze a CP, electrochemical experiment, the way how you analyze it doesn't really change ever. So why not have a standard function that you can maybe tweak a little bit, but this way we know everybody using our software internally, we know exactly how the data points came about, and we really, we even made it simple for people. So in the sense of you could load in a plate map, you could do some simple visualizations quite fast without much overhead. So again, I think having nice tracking of what you're doing in the lab, how your data is coming about is all nice, but you really need a usable user interface. And to be honest, which my group right now doesn't have. Right now, you need to know how to code. But especially when you talk to other chemists, which we do a lot, then you need to think about how can we enhance the user experience. So we do high throughput, and we do this somehow accelerated. So a little bit the question is always, what is high throughput really, and what is high throughput not? So we have experiments such as some of our catalyst experiments, or even some of the battery experiments. Testing a cell will take you somewhere between 3 to 4 weeks. Some of these tests can even take months, simply because you can do the calculation easily in your head. If you do a battery test at 1C, 1D, meaning you charge it in 1 hour, you discharge it in 1 hour, and you need to do 1,000 or 2,000 or 5,000 cycles, you're at 10,000 hours. 10,000 hours is a lot of weeks. So it's about a year until it's done. So is this high throughput? I don't know, you tell me. What I think is more important than thinking about, okay, how fast are we? Is everything going to be like in 1 second? What is more important is that you set up your instrumentation and your software backend in a very agile manner, meaning that if tomorrow somebody comes and is like, hey, I now no longer want to build non-aqueous batteries, I want to build aqueous batteries, that you're not going to be like, oh, we can't do this, but you can adapt to new kind of experiments, and that you can adapt to new parameters more quickly. And then if you have this standardized, I think you can start to call yourself high throughput, even though you might not have automated 100%. If you have some level of agility, what you can actually do is you can do this whole thing called reinforcement learning or active learning. We have this one reactor. We have, in fact, 8 of them. Problem is, and this, I don't know if you want to call this high throughput or not, but one run costs about $300. So here the goal is not to have as many as possible to burn through our consumables money as fast as we can. But here the name of the game is, how can we do as few experiments as possible? Yes, it's still high throughput, but we want to do less. So the idea here is that we have some way, for instance, with some machine learning in the back, that we can have an acceleration or an enhancement. So the issue that I always have when people talk about, we do accelerated research implies that there's a speed of research. So speed, and as a physicist, what is speed? Speed is the change of position by time. Yeah. So how do I measure speed? Where am I? So what I think most of us will probably care about how many experiments you do, because number of experiments roughly corresponds to cost and time. So what we then defined is we have an acceleration factor, where the acceleration in our case is what factor of fewer experiments do you need to get to the same performance metric? Because sometimes your performance metric is just better. So how to measure better? Sometimes hard. What we did in a couple of benchmarking cases is we already mapped the entire response surface, and we just said, okay, we just count whenever we find something from the top percentile, and we count how many, like either with what probability do I get a sample from the top percentile. This is simple because it's from the top percentile, so the probability by just guessing is 1%. And the other thing is sometimes you don't necessarily, it's not always the case that fewer experiments also mean less time or less cost. Think about a 96 well plate. It doesn't cost you necessarily much more time to measure half of your well plate or the entirety of it. Or let's say that cost is not really relevant. But let's say if you have a fixed kind of experimental budget, we talk about the enhancement factor, meaning how much higher is the probability of you finding a good sample or a good process. So how does this whole thing work with active learning? Basic idea is if you have 2 points, you measure them and you assume that nearby your point you have a low uncertainty. So where should you go next? You can either do a space-filling design. So in this case, it would be right in the middle. Or you simply go there where your model that you train is the most uncertain, or you do a combination of both. That is, you try to have a space-filling design where you also reduce overall model uncertainty. So if you do that, empirically, what we find is you can get an acceleration factor of roughly 10 to 30 times, which is still crazy because think about the fact we typically do 2,000 experiments. If you do this, if you just do a 30th of this wouldn't, like, for me, this wouldn't even be high throughput anymore. So you can almost do, a couple of dozen experiments manually. So what you essentially do here is you measure, you inquire your model, hey, where should I measure next? Where are you uncertain? What is the space-filling design? And then you repeat until you're satisfied with the result. This is for the improvement of functional properties. It's much, much harder to reduce the number of experiments necessary to train any kind of model from which you want to learn something with less experiments, because there turns out random sampling is typically the best. So having active learning or reinforcement learning for good models is a topic of current research. So just to show off one quick result, this is 80 data points we did together with Forschungszentrum Jülich for electrolyte conductivity. And the model, what this should just say is the model here is crap. It doesn't predict anything. Then we add 10% additional data, and these individual trained models line up just perfectly and actually find a good maximum. We can deploy this to different experimental setups. So this is to find a new fast charging anode material. So all the batteries that you use from day to day, they typically have graphite on the anode. But graphite is relatively slow with its kinetics. So we tested here some tin, germanium, and silicon based anode materials. And what Alexei was then deploying here, instead of measuring essentially all the points there, which is about 300, we just had to measure 20, 30 points to actually find a a new anode material for very fast charging materials, and we were even able to scale this up. One small advertising, Alexei is going to finish his PhD thesis in the next month. So if you're looking for a really, really good scientist and engineer to do high throughput experimentation, here you have one. All of this is to say, if you have your machine learning models and you deploy them to an automated kind of setup, I honestly don't care how good it is. I care more about where does it fail, and if you can explain me why it fails, then I'm really happy. Because what we do in active learning is we actually, we do, if you really think about it, we do the craziest case possible. So typically, you know, people do whatever, 70-30 split or whatever. What we do here is we do a 199 split. Yeah, I'm learning with like 2-3 examples, and then I'm boldly saying, okay, now I'm predicting for the rest. And I'm really always testing my model that it always fails in the most constructive manner. Because that's the interesting part. You want to have your models fail constructively so you can improve them. So again, I don't care about you know, models that achieve whatever R squared of 0.99. They really need to generalize. And if you test this in a active learning kind of setting, then you typically have this case where no model really generalizes well. So now I talked a lot about what I would call vertical integration, meaning I have an experiment and then I now need to translate this to some motor moving. So stop with that. We no longer do horizontal integration. We do vertical integration. So what is vertical integration? Vertical integration is this whole thing of, you know, collaborating with other labs. For me as an experimentalist, I like to collaborate with theorists because they can do things that I can't, or they can see things that I can't see. Vice versa as well. There are things that are hardly accessible to me that are super simple to just, like, for instance, a pair distribution function. I can't measure it in my lab, but somebody who knows how to do a molecular dynamics simulation, they just, you know, it's a byproduct. So how does this whole thing work? We have two kind of software frameworks in my group. One is called Finalis, one is called Hello. So Hello is this whole thing of vertical integration. Essentially, I want to measure, I want to make a battery, do it. Finalis is this whole thing of, hey, I measured the anion and cation mobility of some electrolyte, but now I need a pair distribution function from somebody that does MD. How do I communicate with that person? It even starts at things like, we experimentalists, we typically work with molarity. MD people work with molality. Yeah, so one is mole per kilogram, the other is mole per liter. It's not the same. You do small mistakes. And if we start talking about, you know, minute differences of less than 1%, it starts to make issues. So what we did for Finalis is we had this whole idea in Big Map that we wanted to have an experiment trigger a simulation and a simulation trigger an experiment. At least this is how we sold it to the European Commission. You need a couple of things besides that. You need, of course, you don't just like want to have a ping pong back and forth. You want to find out something, you want to improve things. So we have an optimizer. We need some database where we need to store the data. We also have a degradation model. And because before we mostly just cared about the experiment of like translating this into a sequence of events and action, a driver, and then maybe some feedback. Now, why do we need two kind of softwares? Hello is hierarchical, so meaning I send data, I send instructions. Talk to anybody who's just mildly related to IT security, they will not allow an incoming connection to a supercomputer. They will not allow an incoming connection to some industrial device. They will just be like, no, we have a firewall, and that's where it ends. In Finalis, we solved this and the fact that, I mean, come on, all of you have been in a higher not high, in a larger research consortium, typically if you play this game of having a workflow with 5, 6, 7, or 8 different participants, you're playing this game, which we call in German Stille Post. Yeah. So I tell you something, you tell the next person, and then at some point it gets lost. You're always just as fast as the slowest link in your chain. So how can we break this? What happens if somebody who, whatever, needs to build batteries, their lab burns down? How can we replace them? What happens if some queue at some supercomputer is completely full and we need to shove off that work to somewhere else? What we said is, but pretty simple, we forbid any direct communication. Sounds weird at first. Hear me out. If I have an experiment directly talk to a molecular dynamics simulation, the issue here is that the moment a degradation model should come in, I need to define essentially if n is the number of participants, I need to define n squared minus n divided by 2 kind of, n squared by 2 minus n interfaces. This never works. At least in my opinion, this experience has never worked. So what we said instead is, nobody directly communicates with each other. Everybody, if you want to have an experiment performed, you send us off to a broker. And the broker has a schema. We implemented this with Pedantic. That says, okay, if you really follow the schema, I promise to send it off to someone, and they promise to fill out the schema like this if they have the result. So essentially, every participant now needs to define 2 kind of schemas. One, if you want to have something from me, this is the information that I need from you. There can be optionals and non-optionals. And this is the schema that I promise to send back to you. Cool thing here is, this is completely agnostic to what kind of workflow manager you use, what kind of lab automation you use. Even if you don't have any lab automation and you do everything by hand, in the end, it's a schema. I mean, come on, you can fax this if you want. So it's relatively fast. So on my laptop, I can handle about 4,000 requests per second. So usually works. What we used this for was a workflow where we really wanted to show that this is intention agnostic. So what does intention agnostic mean? Typically, you set up a workflow to do one thing and one thing only. What I really wanted to show here is, hey, I can do 2 things at once, because if I can do 2 things at once on the same hardware in the same kind of workflow, then I can also do 3, 4, 5 different other things. So what we did here is we did an optimization for electrolyte conductivity and for longevity of a cell. Most scientists in the battery field will tell you, it should be related. Maybe it's even the same. Turns out it's almost the same, but not exactly. It's a nice outcome if you say like, hopefully it doesn't come out at the same maximum, but they kind of do. So all of this is to say, we can now orchestrate research workflows in experimental labs, in computational labs, in machine learning groups, and we can interlink all of this. This here, even though it's just one major figure, took, I think, in total 6 different partner universities scattered around Europe. And this was really running autonomously, meaning nobody touched the system, spanning a few European countries for, I think, about 2 weeks. So, and now we work on better protocols and parameterization. So last thing, and then I should be done, hopefully. So what did we really discover for like new things, and what are some insights that we were able to generate? One cool new thing, and the preprint is out now, and the patent as well, is we discovered a protocol for formation. Formation is something that you as a customer really don't know about usually. So this is the last production step in a battery factory. This is the initial charging of a cell. So there you synthesize the solid electrolyte interface. This process takes somewhere between 24 hours to 48 hours. To put this into contrast, making a cell takes less than an hour. So it's really the slowest process. And if you go to a larger manufacturing site, it's about 1/3 of the factory floor goes to the formation. So if we can increase the speed of formation, and you can't just do it by charging faster, that just doesn't work. If we can increase it by a few percent only, we can make gigafactories smaller and by a significant amount. So what we found out is that by essentially using a super old approach called pulsed formation or pulsed charging, but nobody ever did this on graphite anodes. So we just did it, and we found also with some active learning a process that can be as fast as 8 hours. 8 hours versus 24 hours is insane. This is why we patented this. Now, the issue is people can show you a lot of things on like coin cells, and everything works on a coin cell, but scaling it up to larger format cells is kind of hard. We overdid it. So this is an example on so-called PHEV1 cells. PHEV1 cells have, in this format, 30 amp hours. So these are really big, bulky batteries, roughly the size of an A4 sheet, of course, thicker. Essentially, most of the plug-in hybrid electric vehicles, this is where PHEV1 comes from, have that exact format of a cell, also called prismatic cells. So what we found was, okay, we don't really see a difference. We actually see a slight improvement on our coin cells. So these are the cells that die really quickly. You don't want, after 300 cycles, a dead battery. But if we scale this up to, I think in total 5 or 8 PHEV1 cells, they actually do cost quite a lot of money, simply because they're big. We can see that after 300 cycles, we really see no difference between the pulsed and the CC formed cell. Again, for the pulse charging, we save about 50% in time, and we are well above 95% relative discharge capacity after 300 cycles. If you have an electric vehicle or you're thinking about this, we design cells so that they can sustain about 1,000 cycles or more. And then they are not dead, then they're at 80% capacity, meaning you can easily run most electric vehicles for about 400,000 kilometers, 500,000 kilometers before we as battery scientists would consider the battery to be dead. I don't know how many of you actually have a car with 500,000 kilometers down, probably a few. We also asked ourselves, we do these like super long tests. Can we reduce the time a little bit? Yes, we can. Together with some industry collaboration with BASF, we were actually now able to build a machine learning model that can predict the lifetime for any chemistry in any cell format at any discharge rate, at any sequence length. Is even uncertainty quantified. The only problem is it's not physics grounded. So it will happily predict Coulombic efficiencies above 1, which is unphysical. So I'm already a little bit over my time. So what is next? We are in the process of rethinking how we make materials libraries. So typically you have these gradients, from like green to red. But with a shadow mask, we can actually produce or access much larger coverage regions than before. So now on arbitrarily small substrates, we can actually make complete materials libraries. So we are talking about materials libraries that are no longer 100 millimeter in diameter, but that are like 2 or 3 centimeters only in diameter. So they should technically fit into some electron microscopes. We are also in the process of building combinatorial processing libraries. This is part of the Helge Stein catalyst discovery lab that we set up. So here we use laser flash annealing to make on the micrometer scale different annealing settings. We are very actively in the process of not just doing lab automation and coupling this with simulations. We are also trying to bring in the whole business process modeling side of things, so such as job shop planning, meaning that we can really go towards 100% machine utilization without, let's say, without stressing out. And this is all very intertwined. The big problem with all of this, and this is just some code that runs the scanning droplet cell. The problem with all of this is it becomes complicated and relatively slow, relatively fast. So up until now, 100% of the code that my group is writing is in Python. The only issue is once you need to talk to hardware that it's more on the industrial side, your programming looks like this. This is not LabVIEW. This is a ladder diagram. This is one of the IEC normed programming languages. Python is not, C is not. What this thing really does is it starts a motor. And while the motor is starting up, it first has a red, then a yellow, and then a green LED turning on. That's the code. So I teach an industrial automation lecture, and this is one of the examples. So what my group is now slowly transitioning to is we want to transition from Python with our Finalis and Hello kind of framework to Rust. Why Rust? Rust has this great appeal of being now, for the first time in probably like 30, 40 years, a programming language that I can deploy to a microcontroller. And with that, I can directly compile to WebAssembly and have, you know, a website talking to a microcontroller, essentially, all in one code base. It's super hard to train people first in Python, and then you tell them, oh, but you know, Arduino is more like a C variant, and then now you need to learn JavaScript. I think, from a didactic perspective, a little bit better to do this in Rust. And now that you know, we are now increasingly working with people from the electron microscopy field, or in general, people that have much more data than we have. So we generate maybe half a gigabyte of data per day. If you then suddenly work with people that generate gigabytes of data per second, you need to go to different means. And this is the logo next to the Rust logo is the Apache Kafka symbol. So we are slowly but surely going to transition Finalis to a Kafka backend. Right now it's Fast API, but Fast API is just simply too slow. In a week, we will have the first international Finalis developer conference. And then we will try to negotiate a roadmap towards the transition towards Kafka. And with that, I would like to thank you and my awesome team of roughly 20 people. And with that, I would like to ask you if you have any questions. And if that is not the case, let's have lunch.